this video, our focus is on the Williamson ether synthesis. In this problem of our problem-solving session, we're asked to find a metal alkoxide and alkyl halide reactant that will yield the indicated major organic product via Williamson ether synthesis. Before we get into the actual problem, I want to give you a little review of the key highlights of Williamson ether synthesis. In Williamson ether synthesis, what we are going to be reacting is a metal alkoxide, meaning that we have a metal such as sodium, potassium, or any other atom from the first column of the periodic table. That's going to be our cation, and engaged in an ionic bond with that is going to be our oxygen anion. That oxygen is bonded to an alkyl group. And the business end of this molecule is our oxygen atom that's bonded to the alkyl group. The metal is just along as a spectator. It observes the reaction, it's required to be there, but it does not directly participate. So our oxygen anion is able to act as both an excellent nucleophile, using its lone pair of electrons to attack a carbon atom. It is also a very basic atom, and that has some implications about the outcome of the reaction here that we'll get to in a second. So for Williamson ether synthesis to take place, what we need is for the oxygen atom to act as a nucleophile in an SN2 type reaction where the oxygen nucleophile comes in, attacks the electrophilic carbon as the leaving group leaves. And that reaction will then yield a new carbon-oxygen bond between the alkyl halide carbon and the oxygen from the alkoxide to give us this ether product. Now, there's some caveats that you need to be aware of here, namely that in order for this reaction to work effectively, you generally need a non-sterically hindered primary alkyl halide here. If the alkyl halide has significant steric hindrance, such as a secondary alkyl halide or tertiary, what's going to happen is that due to the fact that this oxygen can act both as a nucleophile and as a relatively strong base, if you have steric hindrance going on here, that is going to make the carbon atom that's bonded to the leaving group not particularly accessible by the oxygen atom that needs to come in and attack it as the leaving group is leaving. So what would happen instead is that you would get an E2 elimination reaction going on where the oxygen atom that is a relatively strong base grabs a beta proton, making it classified as an acid-base reaction to give an elimination E2 product. So we want to design these reactions up top here so that we are always reacting a primary alkyl halide with whatever alkoxide we want. So our flexibility in this reaction comes in the structure of the R group, the alkyl group that's bonded to the oxygen. We're not very flexible about this portion where we have the alkyl halide. It has to be a primary alkyl halide. So when we are looking at and thinking backwards about these reactions and thinking about what can we use as our starting structures here to synthesize, for example, the ether compound up top, we need to think about what we're doing here. We are creating a new carbon-oxygen bond between the alkyl halide carbon and the oxygen of the alkoxide. So when we look at our structure up top here, we have a carbon-oxygen bond here and a carbon-oxygen bond here. One of those bonds goes to a secondary carbon. The other goes to a primary carbon. And in keeping with the theme that was necessary down here, that our alkyl halide had to be a primary alkyl halide, we want to make this side of the equation derived from the alkyl halide starting material. So I'm just going to write derived from Rx to give myself a little bit of note there about what I want to do here. And then our primary carbon, we would have our CH2 bonded to our halogen leaving group, and then there's another carbon of that chain of the alkyl halide. So the portion of the molecule that I've just assembled here as my alkyl halide is this CH3 group right here, our CH2 group, and then our oxygen is going to come in from our alkoxide. So we've got our 2-carbon chain there corresponding to the 2-carbon chain of our alkyl halide. And then for our alkoxide, we have our 5-membered ring directly bonded to the oxygen atom. So that corresponds to this 5-membered ring, directly bonded to the oxygen. And then our oxygen, we could show that as an anion. And our sodium or whatever other column 1 metal you want to use as your cation there. Or you could have just written that out as ONA. That would be fine as well. So to confirm that we will get the right product here, I like to write out a mechanism. And this is an SN2 reaction, which means the nucleophile oxygen comes in and attacks the electrophilic carbon that's bonded to the leaving group at the same time that that leaving group is breaking away. And so indeed, that green electron pushing arrow would be creating the carbon-carbon bond that we're showing here in green in our final product. So let's do this same sort of strategy of thinking backwards here, going from our product to what reactants we would need there to synthesize this ether molecule, tert-butyl methyl ether. So in this structure, we go back and we dissect again like we did up top, and we ask ourselves, which side do we want to originate from the alkoxide, and which do we want to originate from the alkyl halide? And to find out which side needs to originate from the alkyl halide, you want to look for the side that has the primary carbon. So it's going to be the right-hand side. Left-hand side has a tertiary carbon there, so that's definitely not a good candidate for the alkyl halide side of the puzzle. So we have our carbon atom right here. It's just a 1-carbon chain there, so I'm going to make a 1-carbon alkyl halide. I'll do methyl bromide this time just to mix things up rather than always using a chlorine. And then we come over to here and we have our tert-butyl group that was directly bonded to the oxygen. That's what I'm going to plug in as my nucleophile by placing in that oxygen anion right there, like so. And we need a cation. I'm going to use potassium this time just to mix things up a little bit. And much like before, to make sure I'm getting the right product out of this, in an SN2, nucleophile attacks the positively polarized electrophilic carbon as the leaving group leaves. And that will create the new bond that we have in green here in our structure at the left, making a connection of a 1-carbon chain to that oxygen that was right here. We bring in that 1-carbon chain right there as the leaving group leaves in this Williamson ether synthesis. So in general, at this point, when we look at reactions, you should be comfortable going in either direction, meaning you should be comfortable if you are given a final reaction product to indicate what reactants you could use to create that final product, much like if you were in an organic synthesis lab and you had a valuable target molecule such as a candidate drug and you were asked to synthesize it, you should be able to look at the structure you aim to create and determine what reactants you would need to do so, like what we've done in this example. You should also at this point in the semester be able to take a combination of 2 reactants and predict what the product would be, meaning that you should be able to take alkoxide that I would give you, plus an alkyl halide, and propose what the Williamson ether product would be of that. Or if the reaction is set up so that you have a methyl alkoxide plus a secondary or tertiary alkyl halide, you should be able to give me the elimination product of that reaction, because remember, there's only primary alkyl halides that undergo the Williamson ether synthesis. Secondary or tertiary, sterically hindered alkyl halides will instead give elimination reactions to yield alkene products. And if you need to throw back to that, take a look at chapter 7 where we did lots of E2